welcome. Let's so previously I promised that I will talk about a ramp generator circuit because ramp generator is essential in oscilloscope to get the time based circuit, okay, and also in linear ramp type voltmeters we have studied. So there are many applications, and I promise that I will talk about this. And since we are studying transistor based circuits, so I will also have a transistor based, somewhat transistor based implementation of ramp generator. Okay. Okay. So let's start. Let me first tell you the idea, the block diagram, schematic, then we will go into detail. The idea is that we will take a constant current source, and so this is a constant current source, and this we will use to charge a capacitor. This current is constant, which means the voltage across this capacitor, call it V C plus minus, this will increase linearly, right? Why? Because the voltage V C, it is given by C is equal to Q by V. So voltage is given as total charge divided by the capacitance, and the charge is given by this current I multiplied by T by C. So this is proportional to time, okay, because I is a constant, C is a constant. So this voltage will increase, therefore at this point this voltage increases linearly. So this is actually one part of our ramp. I mean, we know the ramp is basically a linear voltage, then it falls down and again linearly increases and so on. Now we have to essentially realize this discharging or falling of the voltage. So what we will do, we will feed it to a Schmitt trigger circuit, and this Schmitt trigger will activate, say, a switch which could be okay, and so what will happen? I mean, we have seen some similar thing while talking about oscillator circuits, 555 timer, you recall. Okay. So this is not a very detailed circuit diagram, but this is a schematic, the idea. Okay. So the idea is that when this voltage goes up above some threshold, maybe this threshold, then this Schmitt trigger will be turned on and this switch will be on. So now the capacitor will discharge, and it will discharge immediately and quickly. Okay, so this voltage will come down very quickly, and once this comes down, then this voltage comes down, so this Schmitt trigger output will change and this switch will be off. And once this switch is off, so this is off, then the current will again, this current will come and again charge this capacitor. Okay, so the idea is, so let me just write the essential points. The source I, the current source I charges the capacitor C, okay, and Vc increases linearly when Vc goes above UTP of the Schmitt trigger. The Schmitt trigger, in short ST, will turn on the transistor, the BJT. Okay, so Vc will discharge immediately to 0 or whatever, maybe in this case 0. Okay, so it will discharge immediately, fine, and then Vc will come below lower trigger point and BJT will be off. BJT will be off. Once again, the source, the current source will start charging the capacitor. This is the idea. Okay, so now we have, if you want to draw a better scheme, better detail, then we have to give some circuit for this current source, some circuit for this Schmitt trigger, etc. So let's try that. Okay, so current. Okay, first voltage. First, let me draw the capacitor. Okay, and we want the capacitor voltage to change from a, say, from a negative value to up to some positive value. Okay, and we need a current source. Now, how can we realize a current source? We did it when we studied linear ohm meter. Okay, so this, is a constant current source. Okay, let me first draw the current source. I'm taking a PNP transistor, unlike the NPN in the previous case. I can do it with the other one as well, no problem. Okay, and then what I will do, I will take a potential divider. Okay, so to make, if say this voltage is 15 volt, and I want this voltage drop to be, so I want a, say, 5.7 volt drop maybe. So this voltage will be 9.3 volt. Okay, so you can take the ratio of these resistances accordingly. So this voltage will be at 10 volt. Okay, you can take this and now, so therefore, and this R1, so if I take R1 equal to 1 kilo ohm, then this current will be how much? This current will be, this is 5 volt divided by 1 kilo ohm, so this will be 5 milliampere constant. Now this 5 milliampere current I will take to a capacitor. Okay, so this capacitor voltage will increase, and the other side I will keep possibly at a negative voltage. Okay, so I will keep it at a negative voltage, maybe minus 10 volt, some negative value. Okay, so that when there is no charge across the capacitor, this is also negative, this is also negative. So and then it will start to grow from this negative value first to 0 and then to positive. Okay, and this you can keep at 0 volt. Okay, so this is at minus 9.3, fine, no sorry, plus 9.3, so that this gap is 5.7 and this is 5 volt. Okay, so essentially this voltage I want to be constant and this current to be constant. Okay, so now this voltage will increase like a ramp from minus 10 to some positive value. Now I will feed this to a Schmitt trigger. Okay, what kind of a Schmitt trigger is useful? I will take a non-inverting type. Okay, so that when this voltage increases, output will also increase. So I will take a non-inverting Schmitt trigger. This is a non-inverting Schmitt trigger, and let me take this R1 equal to R2. If so, and if these voltages are say plus minus 15 volt, okay, then let me quickly calculate the trigger point, lower trigger point and upper trigger point. Okay, so to do that, if this is 15 volt, so at any moment if this is plus 15 volt, then I want to make it above, if this is, let's start from this, if this is minus 15 volt, I want to make it this point at 0 volt. If this is 0, then the output will change. Okay, so if this is V in, so the boundary condition is V in R2, so this voltage V in R2 minus 15 into R1 divided by R1 plus R2, this should be equal to 0. Okay, I'll just erase, and so from this I can write this is equal to 0, and from this I can write this two are equal. Okay, so from this I can write the LTP, this is the threshold for switching to positive. So upper trigger point is 15 R1 by R2. Okay, so yes, so in this case the trigger point will be 7.5. But okay, okay, what I want is this. Suppose I want the ramp to vary from -10 to +10. Okay, you just see that I'm actually designing the circuit while I'm talking to you. So this is, this is a fact that I want to stress, is that do not try to memorize anything. Try to understand and make things on your own. Then you will enjoy it, you will learn it. Okay. So suppose now I want the output voltage, sorry, the ramp voltage to go up to 10 volt. If so, then I want the upper trigger point also to be 10 volt. So what I want this to be 10 volt. If so, I will take R2 equals 1.5 R1. Okay, if this is equal to 1.5 R1, then this will be 10 volt. Okay, fine. So when this goes to 10 plus 10 volt, then this Schmitt trigger will be activated and its output will be plus 15 volt. Okay, now what we will do, we will use this to drive the base of a transistor base switch. So what we'll have, we will, let me elongate it, minus 10 volt. Here I will take a transistor based switch. Okay, this is at minus 10 volt. If I connect 15 volt, there, we may need some voltage adjustment, maybe. I'm not going into that much detail. So if this 15 volt is applied here, this is minus 10 volt, definitely then this will be forward biased and this will act like a short circuit. We may need some resistance to save it from high current. Okay, that much detail I'm not going into, but definitely this is forward biased, so this current will flow and this capacitor will get discharged. Also, this constant current source will deliver its current at that moment through this. Okay, so this is the constant current source. This part is the constant current source in our block diagram. This is the Schmitt trigger, you know. This is the Schmitt trigger and its upper trigger point is 10 volt. Similarly, the lower trigger point will be minus 10 volt. You can calculate it. Anyway, it is always symmetric. So I know it is, if this is 10 volt, then this is going to be minus 10 volt. Okay, so then let me repeat. A current was coming through this and it was charging this capacitor. So the capacitor voltage went from minus 10 to plus 10. At that moment, this Schmitt trigger is triggered. So the output became positive. This positive output made this transistor for base emitter junction forward biased. So the transistor was on. The entire current flowed through this and the capacitor got discharged. So then this voltage will fall down to minus 10 volt. Okay, this voltage across capacitor will be 0. So this is minus 10 volt. So this point will go down to minus 10 volt, right? So this will come to minus 10 volt almost in no time, because this is almost a short circuit, or it will take very small time. So the capacitor voltage went from -10 to +10, then it came down very rapidly to -10. And the moment it comes to -10, this is also equal to the lower trigger point of this transistor. Okay. Maybe then I keep as a safety margin, I can keep it -10.5, so that it is allowed to come below 10. Even 10.1 or something is fine, so that it comes below 10, and the moment it comes below 10, this output will become negative, -15, and if this is -15, this is lower than the emitter, so this transistor will be off. Once this transistor is off, again this current comes here and the capacitor gets charged. So again from here the voltage will increase. This is the Schmitt trigger, this is the capacitor, and this is the constant current source. We are done. We have generated the ramp. Okay, so we are so happy that we have done it. And now just some small things, as I always do, as I always ask. Okay, question: can we calculate the ramp period? Okay, so can we do that? So for that I just need to know the value of this capacitor. Okay, so very quickly we can do it with these numbers, with this data. If we change these numbers, answer will change. I will use the same number. So this current, this is 5 milliampere. So this is approximately 5 milliampere. So this is 5 milliampere. If this is 5 milliampere, and let's so what is this? So what can I say about the voltage Vc? Vc is, as we already have written, IT by C is, so therefore 5 milliampere multiplied by T divided by C, whatever is the value of this capacitor is C. And from this we know Vc has to go from -10 to +10. Vc has to go from -10 volt to +10 volt, which means if this is my time period T, in this period the total change is 20 volt. So I can write 20 volt, I am doing it very quickly, is equal to 5 milliampere by C multiplied by the time period. From this you can calculate the time period, which is same as 20 volt by 5 milliampere multiplied by C, and the frequency will be 1 over T. Okay. And can we calculate the height of the, this we already have, no, so we need not calculate. So this is from -10 to +10. Okay, so how can we change the frequency, or okay, so you can take a variable capacitance, definitely, because we have C in the expression of the time period. So change C, or else what you can do, you can change this R1, because if you change R1, then this current, you call this current I, where do I write? Okay, I write here. This current I, just this same as this current, is same as 5 volt by R1, right? 5 volt by R1. So if you change this current, definitely the time required for this voltage to go from -10 to +10 will increase or decrease, right? So you can change this, and thereby you can have a controllable ramp generator. Okay, and this here in this circuit we have taken a constant current source which is realized using a transistor based circuit. Okay, thank you. I think this is the point where I will conclude this course. We have gone through a lot of topics. Some of the topics, at least towards the end, I myself felt I had to rush because of the availability of time. But if you feel, if you have any doubt, any query, please post that in the forum. If required, we will make more videos later on if you want. Sometimes we have gone very slowly. This is with the assumption that all of you might not have studied all the required background. So that all of you can understand, I have sometimes tried to go very slow. This course has gone longer than the expected, much longer than the expected duration. And if you have come so far with me, I really congratulate you from the deep of my heart, deepest point of my heart. And sometimes the course was boring because I have gone so slow. I hope the study materials that from the book which I have pointed out, you can study that much quicker without having to wait for this long and delayed boring videos. Anyway, thanks a lot. If you have any query, post us in the forum. We'll try to help. And thanks a lot to all the team members in the NPTEL whom you possibly do not see, but without whom this effort wouldn't have been come up to this point. Okay, thanks to all the team members of the NPTEL. I know how many times I have retaken the videos. They have helped us without getting disturbed, without getting bored at all. Thanks to all of you. Thank you.